Hi everybody, this is going to be the momentum notes and practice problem worksheets. I'm going to do about the page 1.5, and then the next video will do 2 in the lab, and then the next one will do page 3. So make sure you sort of watch all 3 as you go along here, and that way we can go faster in class itself. Inertia is actually, in motion, is actually called momentum. So you know that objects in motion want to stay in motion. Well, momentum is the same thing, except you've got to be in motion in order to get this to work. So inertia in motion is momentum. The symbol we're going to use for momentum, since we already used the letter M, is going to be a cursive P, which is actually pronounced row, as in row, row, row your boat. Now the formula for momentum, there's actually a couple of them, but the one we're going to use is mass times velocity. So if you have something that's really, really massive, like a train, as long as it's moving, it's going to have a lot of momentum. Or you can have something really small, like a bullet, but since it moves at such a fast speed, it's going to have lots of momentum. Change in momentum is called impulse. And that's usually what we're wanting to deal with when you're talking about sports, like hitting a home run or kicking a ball a long way. You want to give a ball a very big change in momentum. Now, there's 2 formulas for impulse. First of all, I'm going to put impulse would be delta rho, because rho stands for momentum, delta means change, and since impulse is change in momentum, I'm going to use delta rho for the formula of it. And there's 4 things we can change. We could take and change the mass of an object or change its velocity. So mass times change of velocity is one formula. And we could also put more force on a ball to give it more impulse or more momentum. And we can change the amount of time that force is on an object. So for instance, you might have heard of a baseball coach or somebody, or tennis coach, something like that, saying follow through. Well, when you're following through, you're putting more time on that particular object. So over here, it's actually 4 ways, not 3 ways, to change the impulse, and that would be by increasing the mass, which usually you don't do, increasing the velocity, increasing the force. I should say velocity. Sorry, I just messed up here. Velocity, force, and then I'm going to add another one, number 4 over here, will be time. Number 7 says, what is the momentum of an 8-kilogram bowling ball moving at 10 meters per second? Well, momentum, remember, is rho, so I'm going to take rho equals mass times velocity. The mass is 8 kilograms. The velocity is 10 meters per second. So I'll take 8 times 10, and that gives you 80. And there really are no units for, or a specific unit for momentum. So we're just going to put those 2 together. It's going to be called a kilogram meter per second squared. I applied for the unit for accuracy, but they're using my last name, Wright, as a unit of accuracy. So I'm sorry, I applied for the unit of momentum, but they gave me the unit of accuracy. Number 7b, it says when an 8-kilogram ball strikes the pins, its speed reduces from 10 to 5. What's the impulse? Well, you got to remember, impulse is change in momentum. Change in momentum is m delta d, because now the ball is going to slow down. So I'm going to put in the 8 kilograms for the mass. The change in velocity is final, which is 5, minus the initial velocity, which is 10 meters per second. So that comes out to a negative 5. So negative 5 times 8 gives you negative 40 kilogram meters per second. So it actually lost its momentum. That should be kilogram dot meters per second. Kilogram times meters per second. Number 7c, if a ball in 7b took 0.2 seconds to hit the pins, calculate the force. Well, I can make one of my little triangles over here. And I know that momentum, oh shoot, my fault. Momentum is, let me erase this. And let me redraw it. since momentum is force times change in time, if I want to find force, just cover up the F, and force then equals momentum divided by time. So I take my momentum, my change in momentum of 40, divided by my change in time of 0.2, and that ends up giving you 200 newtons. Now on the next one, they actually give you 3 different things. They give you the mass here of 0.2, the speed here, the time here, and they ask you to find the force. Well, since we can put all these different impulse formulas together, I could say that force times time, which is what impulse is, equals mass times change in velocity. Again, both of those are the formula for impulse. So what I'm going to do is I'm just going to solve for force. So I'm going to bring this over here. F times my time of 0.5 equals my mass of 0.2. And my change in acceleration, since it's hit from rest to 50, acceleration's final velocity was 50, initial was 0. So now you simply divide both sides by 0.5 and multiply by 2. This comes out, that'll end up being 20. Come on. And since it's force, it's newtons. On the next one, it says a 2-kilogram bat. Well, that's mass right there. Is pitched from a negative 50, so this is my original velocity, and it accelerated to a positive 50. This is my final velocity. If the bat is in contact for 0.5 seconds, that's time. Once again, calculate the force. I'm going to use the same formula again, but this time the change of velocity, just because the pitcher pitched it, it's different. So I'm going to have, let me erase that. So once again, I'm going to have F times T equals M delta V, because both those end up being momentum, or impulse rather. For my time, I'm going to put in 0.5 seconds. For my mass, I'm going to put in 0.2 kilograms, just like before. But now, since the ball is pitched, the final speed is 50. But the initial speed is a negative 50. So it's a little bit different than the one above. So just because it's pitched, 50 negative minus the negative is plus. So 50 plus 50 is 100. 100 times 0.2 is 20. And then 20 times 2 gives you 40. So I doubled the amount of force on the ball simply by pitching it. So pitchers want to make sure that, if they're down in the count or they have lots of balls on the batter and very little strikes, you don't want to throw a high fastball, because that batter gets a hold of it and it's going to go a long way. So what happens to impulse and force when an object bounces, and why? Explain using the basketball and the tennis ball demonstration. So if you notice, when I put the tennis ball on top of the basketball and I bounced them, the tennis ball shoots up to the ceiling, and if you put 2 basketballs on top of each other, do the same thing. The reason for that is the amount of momentum that the top ball gets. When it bounces off the bottom ball, it's going to get all the bottom ball's momentum. The top ball has to slow down, then speed back up. So you got 2 changes of speed, one to slow down, one to speed back up. Changing the speed twice doubles the impulse or doubles the momentum. So bouncing always doubles your momentum change or your impulse. So if a turbine on a hydroelectric plant is straight, let's see if I can pathetically draw this here. If I have a wheel and here's the straight paddles, when the water would come in and hit this, the water's simply going to come in, push down on the paddle, and then fall off. Well, what a guy by the name of Fulton suggested was that you take the wheel, and instead of making them straight, you curve those blades like so. And by curving the blades, when the water comes in, now you got the water coming in here, when it hits a curved blade, it bounces off. So these things, it changes the direction of the water. Well, remember, anytime you make something bounce, you double its momentum. So if you double the impulse, you double the power of the turbine. Number 10 says, why should you follow through on a bat? Well, following through makes the force on the ball for a longer period of time. So once again, the longer you swing that bat, the longer the ball is going to be on the bat, which makes the force on the ball for a longer period of time. That gives it a bigger change in momentum, makes the ball go farther. Now, airbags and seatbelts also pertain to impulse, but in this case, seatbelts, what they do is they make the driver actually attached to the car. And that makes the impulse less, because instead of continuing forward and suddenly smacking your head on the windshield or your face on the steering wheel or something like that, you're part of the car, so you slow down slowly with the car, and the car absorbs the momentum of the crash. And therefore, your impulse is a lot less because you're slowing down at a much steadier rate as opposed to suddenly. Airbags, on the other hand, they increase the time at which the impulse or the change in momentum occurs. Now, you wouldn't think you'd want to increase the time that a crash occurred, but here's the reason why that works. If you take your impulse, which is your change in momentum, and I'm going to have this one is going to be without the airbag, and then, without the airbag here. And then over here, I'm going to have one that is with the bag. Now, both those momentums are going to be the same, because your car, let's say it's going a certain speed, it has a certain mass, so it only has so much momentum. But don't forget that the formula for changing momentum is F times T. Over here, it's F times T. Well, let's just say, I don't know, you had 10 newtons of force. I'm just going to say this over here. You got 10 newtons of force. And without the airbag, the collision lasted 1 second. Well, 1 times 10 is 10. Well, with an airbag, your time is extended. So let's just say you have 5 times as much collision time. Now, I know that a collision in a car would never last 5 seconds, but I'm just going to put it on here for the sake of seeing the math. Well, what times 5 would give you 10? Well, the force is 2. So do you see how with the airbag, there's only 2 newtons of force, but without the airbag, there's 10 newtons of force. And that's why people that are involved in drunk driving accidents, for instance, they sort of ride with the punch. And so therefore, the collision is lasting over a long period of time, which lowers the force. People that are not drunk get scared, they stiffen up, so their time is much less, which creates more force on their body.